Today we're back with another Data Lab video where we delve into network analysis, exploring an economic competition network. We rely on the dynamic competition hypothesis, which, like the TV show Survivor, assumes that alliances are forged and that leaders emerge from this dynamic. We use the same common out neighbor score that the authors of this work used to predict the winner of Survivor, and try to identify leading or dominating economies, as well as the counterpart weaker economies. If, like me, you are tired of AI and LLMs and want to learn something different, then this is for you. Stick around. So first we need some data, and the data I used was the Atlas of Economic Complexity. They already provide several visualizations and analytics on top of their own data, but they also provide the data over here. This is quite a rich data set, but we only use a few files out of this data set, particularly the country trade by partner, which covers bilateral trade. Each product is classified using HS92, which is an harmonized system for product coding. This is used worldwide by customs agents and officials to track products by category in a common way. You get different granularities, so we are using these files by partner and product, and this 6-digit product level refers to the granularity of the HS92 code. You can have 2 digits, 4 digits, 6 digits, depending on the number of digits the product is classified with more granularity. So you can, for instance, get a code for meat, or you can get a code for bovine meat, more specific. The more digits you get, the more information this number will give you. We only have this with 6 digits, so this is what we use. And we look at data. As you can see, each file is for a different range of years. We only look at data for 2020, 2023 specifically. And then we also use the two files with product and country metadata, so the country classification 1, as well as the HS92 product classification 1, and these just contain information about the countries or information about the products. So like last time, we are using Data Lab to ingest this data, and we'll be doing this based on DBT and Duck Lake, just like before. If you don't know how this works, you can watch my previous video on this topic. But either way, this time we added a new way to ingest data set, and in particularly we added something that we call templates. And so a data set template essentially is a definition of a list of dataset file metadata, and this is just a data class that contains a source, which can be, as defined over here, it can be a file name, a URL, a table name, etc., and the target destination, which is usually a path, and it can be, a table name within a Duck Lake or something like that. We also track attribution so that we can, comply with legal requirements. Each time one of these data sets is used, the attribution text will be printed within the terminal. I think that's quite fair to do so, since this data is provided for free. And then we have a specific implementation over here for the Atlas of Economic Complexity, which is compatible with the Dataset API. So in essence, we just added compatibility for any Dataset API dataset. And essentially what this means is that we can just define this template property and several dataset file metadata. The sources are the DOI URLs for the file. The target directory will be the local rankings directory, which is just a temporary directory before we move it to the S3 bucket. And then we have the attribution text, and we have this for several other files as well. We just ingest all the files, and then we, during ETL, we just transform the ones that matter to us as usual, and you can check my other video on the topic. But just to give you an overview, under transform models, and this transform is just a DBT project, we have the stage for the Atlas of Economic Complexity, where we ingest the three tables I was just talking about. So the country metadata, this is just, you know, a trivial ingestion, nothing too fancy over here. We've got the trades themselves between countries and partners, and we needed to add this null string over here. Some of the entries were failing to be loaded, so we needed to, you know, replace a few values, but nothing too major. Same happened over here. This is just the metadata for products. We get a bunch of information. We are mostly using the short name for displaying the product. And then we compute a bunch of analytics on top of this. The main one is perhaps the CC metrics model over here, which computes the Export Similarity Index. So essentially we just group by country and product and compute the total export value for a product, and then based on this we compute the share of each product within a country. Okay, so we just as you can see over here, we partition by country ID, and we compute the fraction of dollars that this represents in the country's economy, and then we do this for every pair of countries, from the one with largest export value to smallest export value, and we just compute the minimum between each of the shares, which gives you the ESI, and this will in turn give us a graph. Let me just quickly show it how this works. So if you want to learn about it, you can just go to the Fed website, and there is this article on the sectorial evolution of China's trade, and they use the ESI for this. I do not multiply by 100. This is, you know, fraction or a percentage, and then you have the, you know, for each country, and I is the product. You'll be iterating over each product that is commonly exported by the countries. So country A and country B, product I. This will give you the, you know, the export value for this product. This will give you the total value of exports for the country. And so, for instance, let's say that a given product is 50% of the economy of a country, and it is only 30% of the economy of the other country, then this only contributes 30% to the ESI. And this is a very basic metric that works quite well to, you know, capture competition. Then we could have, you know, cut this for a given threshold, but we ended up including all of them, with the idea that we might use this weight, you know, in our metrics to you know, dampen or boost a given metric. We ended up not using this, but you know, this is available over there, and if you'd like to export this further, you could have access to it on the graph. And so going back to VS Code, Once these metrics are computed, then we do the final transformations for nodes and edges for our graph, and we'll get countries and products, as well as competes with edges, which are based, like I said, on the SI. Okay. And finally, we'll get the exports and imports edges, which are between countries and products. Another thing that we added was the graph analytics package, and this is to store any metrics that we want to compute, might want to compute multiple times. And one of the metrics that we use here that is central to this work is the common out neighbor score, so con score. So we implemented this as a permanent option of Data Lab. So for any graph, you could essentially just compute this score. You just need to send it the node label, the relationship label, and the target column name where to drop this score, and this will be dropped within the given node table. I will go into more details on how to compute the common out neighbor score, but essentially we are basing our work in this Centrality in Dynamic Competition Networks paper, which is by Bonato and et al. And in here they find the common out neighbor score. This work is also an extension of the previous work on the dynamic competition networks, detecting alliances and leaders. And this is particularly more focused on Survivor and Big Brother as examples, which are really great examples of social dynamics. And over here they also they had already defined this score, and this is quite a simple score. So let's start with this formula over here, which is for a set of nodes. We only just compute this between two nodes, but for every pair on that set, you just compute the number of common neighbors that they have. So for each outgoing edge, this will lead into a neighbor for a node. You fetch the neighbors for both nodes and just do the intersection between those sets. And then to compute the common out neighbor score for a single node, you just iterate overall common out neighbor scores for pairs of nodes for each neighbor of that node. And this will give us a metric that is a good indicator of the leadership of that node. And for our particular case, where we have a graph network of countries, this will tell us which countries are more dominating or leading regarding their economy, and which are a bit weaker or less dominating. Finally, let me just give you a brief overview of how we load this data from scratch and run the ETL pipeline if you want to run this yourself. So I'll be providing a notebook called econcomp under the notebooks folder of the Data Lab repo, and link will be in the description. And if you want to ingest the required data into your own Data Lab infrastructure so that you can run this notebook, just go over here and uncomment these commands, and this one will ingest or download the dataset based on the Atlas template and create a new dataset called the Atlas of Economic Complexity. This will be dropped onto your S3 ingest buckets. And again, please refer to my previous video on DBT and Duck Lake, where I describe this in detail. Then we'll run the transform command, which is just a wrapper for DBT, and we'll run it for this model and the dependencies as well. So this will produce the necessary Duck Lake tables with node and edge data. Then we'll export the econcomp graph that was generated over here, export it into Parquet. Finally, we'll load the graph. And this means that we are producing a Kuzu DB locally that we can use and will be using throughout this notebook. And finally, we can call the new computation for the con score, where we just give it the graph name, the schema name, the node label and the edge label. So we will compute the con scores for the graph of country competes with country, essentially. Now I've already loaded this graph into Kuzu, but before we delve into the Jupyter Notebook, let's first take a look at the graph using Kuzu Explore. And so if we go into the schema, we'll find that we've got a node with country, where country competes with country. Okay, each competes with edge will have its corresponding ESI, so it's Export Similarity Index. For each country, we'll have all this metadata, which comes from the country classification file, and then we'll have an aggregated node for exports of products and imports, so country exports product will have the amount of product exported, we'll have the amount of product imported. We just don't know which country is exporting to which country. We could model it that way, but we are not going to look at that network at this time, and just having the imports and exports will give us a proxy to supply and demand, which is quite enough if we are focusing on competition between countries. Let's just take a look at this graph, at 10 nodes on this graph. So for instance, we've got a country, most of them are competes with. We will have, for instance, American Samoa, which is competing with only 5% competition with Palau. Okay, 7%, 8%. So this is not highly, 12%. It's not highly competing country, but we could, for instance, country name short, and let's look at, for instance, the United States and of America, and in here we have 10 of the competing countries with the United States. For instance, in here we've got 45% competition with Italy, or 45% competition with Singapore, and this is the data that you should expect to see here. You also should expect to see exports data. For instance, for the United States, you'll have this amount of dollars exported between 2020 and 2023 of, let's check it, balances of a sensitivity of 50 milligram or better. I have no idea what this is. For instance, we've got pipe alloy steel over here, and we are looking always at the short name for this. As you can see, you have the 6-digit HS92 code over here, which gives you all these details. Metal work, time switches, all the products will be displayed over here as well. So this should give you an idea of what the graph we are working with looks like. Let's just take a look at another utility that we have available to use with the notebook, which is this new graph visualization package. In here we have a color palette that matches the colors of our channel, and we've got a bunch of useful visualization functions. The two main ones are plot, which helps us plot a graph using NetworkX and Matplotlib, with a bunch of good default parameters for what we are trying to visualize. And we also have the plot map function, which uses the GeoPandas to be able to plot the countries in a map using the ISO A3 country code, which is sometimes better than looking at a subgraph, especially when you have a complete subgraph where all countries are connected to all other countries. So there is a minimum level of competition between all countries, and this gives you no real information. So looking at the map is just better. So you don't have to use graphs all the time. You just use graphs to take advantage of things that are modeled by the relationships between nodes, and you cannot extract or visualize in other ways. And so let's now go into the notebook. So let's begin just by looking at the sections that we are going to cover within the notebook. And yes, I am using VS Code for this. It works quite well. I do recommend it. As you can see, you get the table of contents, and everything works just like if you were using Jupyter Notebook out of the browser, with the added advantage that you can use all the typical VS Code features like refactoring and all that. So first we split this into just 3 sections: the setup one, the analysis, which is the main section, and a few comments or closing remarks. For the setup section, as you can see, we have the ETL commands over here. Then we import a bunch of required libraries. The main ones are Kuzu, NetworkX. We use it a bit, not too much, but mainly under the visualization package. We also use pandas a bit, but that's about it. Then we just ensure that our GraphDB had been created over here, and we just initialize the database. We'll be using this con object throughout the notebook. We also set a bunch of constants over here, and this is just the matplotlib palette so that we can reuse it if required. And we also set the label properties for country and product, so that when we are displaying the country node or the product node, we use one of those properties as a label, and just for visualization purposes. Then we've got a few helper functions like print query, which just takes a query and loads the parameters into the appropriate variables, so that we can just copy and paste this query under Kuzu Explore, for instance, just to help us debug. It would be helpful that we could just set parameters on Kuzu Explorer directly, but for now this works fine. Then we've got the Jacquard similarity function, which is just a set similarity function. It's the number of intersected values between two sets divided by the number of the union of both sets, so the cardinalities. And this will be used to compare, for instance, baskets of products exported by 2 countries or 2 clusters. Then we've got a top function based on a given column, which we just use it for when we compute the total amount of exports or imports per cluster, and we want the top 10% or the top 25% most exported products for that cluster. We can use this function. And then we get into our analysis over here. There are 2 main parts to this analysis. One that we call the dynamic competition analysis, where we just identify the dominating or the leading economies and weaker economies based on the con score for each country. And we also look at the trade basket overlap for the top and bottom economies. Then we just look at the competition network directly, which means looking at the competes with a relationship. so we use that projection. Sometimes we also characterize some of the nodes based on the exports and imports edges, but mostly we are focusing on analyzing the competition network over here. And we do a community analysis where we include community mapping on the plot map that I just showed you. We look at the top traded products, and we also study trade alignment, and we split this into two parts. One that looks at the trade alignment within the cluster itself, so imports and exports within the community or the component, in this case the community, and also the external competitiveness, which looks at the exports and imports between countries in the community to countries outside of that community. We repeat this analysis for weak components, which essentially weak component will just widen the reach of a community. So it's a whole component of connectivity, and because it's a weak component, we disregard direction. If we didn't disregard direction and looked at strong components, we'd essentially just get singletons, so there really are not that many interesting facts about strong components over here. And then we do a community and weak component comparison to try to understand which countries are a part of which communities and components at the same time, or which are specific just to the component but not the community, and vice versa. And then finally we look at economical pressure. We do this based on PageRank. It's a very straightforward application of PageRank, but quite an interesting result as well. And so let's begin by taking a look at the dominating and weaker economies based on the common out neighbor score. This was already pre-computed on Graph Analytics when we did the ETL for the graph, and we can look into more detail at what this is particularly doing. So it creates the property con_score on the appropriate node table. It then resets that property to 0 and computes the common neighbors for nodes A and B. So this should be countries, competes with another country, and this country should match, so hence the common out neighbor. We just exclude the nodes, or rather out neighbors, when A and B are the same node. Then we compute, we have a slightly different approach, and instead of just counting the number of out neighbors over here, we use the additional information that we have with the Export Similarity Index, and we use that instead, and we sum over that instead of counting, and then we just compute the regular con_score for node A, and we set this as the property on the con_score column. And then we can just directly use that con_score on our graph, and if we order in descending manner by con_score and we get the top 10, we'll just find the top 10 dominating economies, which were identified as United States, Canada, United Arab Emirates, Netherlands, United Kingdom, Belgium, Italy, Spain, France, and Thailand. And then we look at the top 3 exports for each of these countries, and again we can do this with Cypher based on our Kuzu database, and we now plot, we use our visualization model to plot this graph. As you know, with Kuzu you can get the result as network X, and we just take advantage of that, and we plot this graph over here, which shows you the top 10 dominating countries with dominating economies, as well as the top 3 products exported by each country. You can see 3 edges going out of each country, and we can find stuff like, for instance, in Belgium we've got vaccines, human vaccines. In Thailand we've got parts of data processing equipment or monolithic integrated circuits, digital, and we also got this special trade data discrepancies node, which sometimes happens where information is not enough. Then, for instance, for the United Arab Emirates, you have gold in unwrought forms, or we've got petroleum oils, crude oil, we got transmit receive apparatus for radios, and for instance, in Spain, we've got distillations of oils, petroleum, and automobile parts, spark ignitions. And as well as medicaments, so medicine. And I believe this is an interesting little subgraph over here. Then we look at the bottom 10 weaker economies. It's similar, but we just order in ascending manner by econ score. And we get number 1 is undeclared, which shows us this. This is a special node. Shows us that, you know, there is a minimum of a small amount of undeclared products that are circulating in the world, but fortunately it's just, you know, small amount of them. And for these weaker economies, mostly you'll find small islands, which due to their geographical area and location are have more difficulty in establishing trade routes and producing a large amount of different products, so it makes sense. And we also look at top 3 exports for these smaller islands, and as you can see, they are fairly disconnected from each other. And we've got a lot of raw materials like molasses or cotton or minerals or coffee, and we've got a few components like automobile spark ignition parts, or abrasive powder grain or other materials, tankers, you know. So this is also interesting. Then we thought, are dominating economies exporting the same products as weaker economies? And if so, maybe that's why those weaker economies are being pushed to the bottom. We don't know. This is just speculative, but at least if we know that this happens, we have a lead towards, you know, that hypothesis. And in order to understand this, we do a visual analysis, and you can check these queries in detail. The code is open source. But I won't go into too much detail over here. This is just tuning for visualization to, you know, reduce the approximation strength of some nodes, and this is essentially the result. We'll find that the top 10 countries with dominating economies are in fact exporting most of these products from the weaker economies, that weaker economies also export. So yeah, there could be some kind of relationship between this, and most likely this is what happens. And just because an economy is smaller or weaker doesn't mean it is in a critical state. It's just, for instance, in this case they are small islands, so it makes sense that they have smaller economies as well. They are more remote, and I'm not, you know, an economist or anything like that. This is just a bit of intuition. And now let's look at the competition network. So country to country competes with, and first we install the algorithm, the algo extension for Kuzu. Then we try to drop a projected graph if it exists, just to have an initial state, and we project the graph into a component named graph, where we consider nodes that are of type country and different from undeclared, and we consider the competes with relationship regardless of any condition. And then we produce this component graph that we can use to plot or query. We also prepare a bunch of inspection functions to plot clusters, and we can plot it as a graph or as a map. And we also have a function that will give us the traded products per cluster. It might be imports or exports. And these will be ordered by the amount that is the total amount that is exported. And we also have functions to give us the partner clusters, which means that if we cluster a bunch of countries together in communities or components, then a partner cluster would be a cluster where the countries within cluster A export to, so cluster B will be partner cluster. This will give us the partner clusters. And also we have a way to determine trade alignment. Trade alignment is basically computed based on the supply-demand ratio. This might be within a given cluster, so there are multiple countries importing and exporting within the cluster. Is the cluster self-sufficient or between the cluster and other countries outside of the cluster? And that will tell us whether the cluster has any export competitiveness. So we compute this aggregated global STR score. We apply a log transformation to this score, just to make sure it's not skewed. And then we compute the weighted average based on the total amount of dollars exported for each product. And we apply the sigmoid function so that we scale this to a score between 0 and 1, and which means that 0.5 global STR score will be the minimum. Everything above that is self-sufficient if we are looking at that, or has export competitiveness if we are looking at that. So now we are going to compute the competing communities. This means that these are clusters where the competition is extremely dense within nodes of the community, but less so to nodes outside of the community. The definition of community in network science is just a dense subgraph, which matches with that definition. So we just create this Louvain ID property. Louvain is a community detection method that optimizes modularity to create a partition of the graph. And we call Louvain for the component graph, and this is already implemented within Kuzu. Then we just look at the countries excluding the undeclared country special node, and color these based on the node classes given by the partitioning. And we don't have a very extensive palette, so this is not easily visible here, but as you can see, there are multiple different communities, and we can look at the sizes of these communities and find that community 5 is the largest community, and we've got about 10 or 11 communities over here. And we can check out the community size distribution. It is fairly common for complex networks to have a huge community containing all the most connected and with higher interaction nodes, and then a few large communities and then smaller ones. Then we can look at each member of these communities from largest to smallest community. As you can see, this is the community containing United States and United Kingdom. So this is probably the strongest economy over here. And then we've got other communities, for instance, including Egypt and Ecuador, Norway, Russia. And we've got a bunch of other communities over here, for instance, the one with South Korea, Taiwan, Vietnam, Philippines. There is Brazil over here. Okay, you get the drill. So you can look at these communities. We fetch the largest community ID, which is 5, and the smallest community by size, which is 10. And we just plot the largest community. As you can see, this time we left in the edges, and this is completely unreadable. This is most likely a complete subgraph, so this is less useful, and this is why we plotted this as a map, and this gives us a much better view of what this community represents. And you can see, for instance, the Iberian Peninsula. You can see the United States and Mexico over here, India, you know, a bunch of Central European and Nordic countries. Then we look at the top exported products for each of these communities. We take into account the top fraction, so we look at the default, which is top 25%. For the largest community based on total amount of dollars exported, and we get 17 or 18 products. And we do the same for exports for the smallest community, and then compute Jacquard similarity between the two product sets, which is only 5%. So the largest and the smallest community have only 5% of exports in common for their main, exported products. We do the same for the imported products for largest and smallest clusters. And as you can see, there is petroleum and oil, medicaments, trade data. Okay, trade data discrepancies is quite large over here. There is gold, there is blood, there is natural gas, and these are, as you know, products of a strong economy usually. And for the smallest economy, we also find oil sometimes, and commodities, parts, jewelry, a bunch of common stuff in this particular case. And as you can see, there is 33% of common products, and these are quite similar because we are talking about imports over here, and obviously if oils are a signal of a strong economy, that when we are talking about exports, it's normal that most countries will need to import that as well. So there is a high demand for these products. Now we take a look at self-sufficiency, and we look at the trade alignment by cluster or internally to the cluster. So we are doing this for all communities of all sizes, and we are computing the global STR score and sorting in descending manner. Over here we find that community 9 is the one with the highest self-sufficiency, and so forth. And we can see this visually over here, and we have the threshold line of 0.5. Curiously, this community 5 is the community that includes, the European countries, the United States, etc. But it is barely under the limit of 0.5, so it is really self-sufficient, but is borderline self-sufficient. And we can look at this community, which includes all these countries like Portugal, Spain, Romania, Turkey, you know, Lithuania. Does it contain the United States? Let me check if it does. So we can check it in this way. I think it's called label over here. And as you can see, this is within community 5, so yeah, it's the same community. Then we also compute external competitiveness. We use the same trade alignment by cluster function, but this time use the inter method, which means it will look at the trade relationships between nodes within the cluster to nodes outside of the cluster. And these values are, you know, much lower than 0.5. As you can see, they are all below 0.5, with community 5 being the one with the highest external competitiveness. But they aren't, you know, particularly overwhelming for any of these communities, and this is expected because our graph is a competition network, and we are computing communities within this graph, which means dense graphs, which also means that within each community we'll have the most intense competition happening, and that competition won't be as visible to outside of the community. So this is just more than analyzing that community, this is confirmation that what we have applied here makes sense. For instance, we already know what community 5 is, so we look at community 8 over here, and we've got Singapore, Malta, Hong Kong, China. So yeah, this makes sense. Then we look at weakly connected competitors, so the weakly connected components, which disregard direction. We can also compute this using Kuzu. And we do a similar visualization. As you can see, there are multiple components over here. And we can also look at the sizes of these components. There are multiple large components, but then also several tiny ones that are completely disconnected. And then we can look, you know, at the distribution of sizes. From here forward, you only have singleton nodes, so they didn't make it to any of the weakly connected components. It's most likely due to the number of iterations that we are using. And we can look at these weakly connected components as we did before, but more interestingly, we can look at you know, the map for this. So this is kind of like an extended community 5, this component. It extends it with Canada, for instance, and several other countries like Russia over here or China. And this shows you, you know, the largest trade connections that we get probably in the world. It includes Antarctica as well. There are scientists over there that need stuff as well, so probably that's the reason why. And then we look at the largest and smallest weakly connected component as well, and look at the exports and the imports. And as you can see, the largest one is about circuits, because now we are including China. That's probably why we've got circuits as the top one export. We'll probably include other countries as well that produce this type of material. For imports, we only get petroleum, oils, crude. So this is really the critical path towards trade within this largest cluster. And if we compare the largest and smallest clusters, we only get about 12.5% overlap in products, and this is largely because we just have one product over here for the smallest cluster. Finally, we also look at the imported products. Petroleum as number 1, circuits as well as number 2 for the largest one, and oils and petroleum for the smallest one, cargo vessels, because remember the smallest clusters are usually islands, so they need cargo vessels for, I believe this should be ships for transportation by sea, and we get about 13% overlap over here. So regarding trade alignment on weakly connected components, let's go directly into the graph. In here we'll find that there is a high self-sufficiency for most weakly connected components, with the exception of these three over here, with 0 being our cluster with the United States and the Western world mostly, as well as China and Russia in this case. So this is borderline, self-sufficiency. This seems to be a sign of a kind of a balanced economy or something like that. But I don't know. As I said, I'm not an economist. And finally, external competitiveness. If we look at this, they are again not that competitive externally, with the exception of cluster 0, which is nearly balanced. Finally, we compare communities and components, just to try and understand which countries are a part of both a weak component and a community, which are parts of just the component or just the community. And in order for us to do this, we just compute the similarity between the largest partition, so the partition with the largest amount of clusters, and this is the weakly connected components, which have 68 components versus 11 communities. So we compute the nearest neighbor clusters over here with similarities that are not that similar. This is good because we know that computing weakly connected components and communities will give us different information, different structural information from the graph. Then we can look, for instance, at the number of times each community is matched with a component. For instance, community 5 is matched 20 times with a weakly connected component, and these are those components over here. And only a small fraction of elements from each of these components is a part of the the largest community. And then we do just set comparison between these two communities. We select, for instance, the largest component, but we could select a component with a given country as well. And I'll run it again with Australia, for instance. And then we transform these countries into sets and compute, the countries that are only a part of the weakly connected component, the countries that are only a part of the community, and the countries that are a part of both of them. So this is intersection over here, and this should give you some interesting information as well. And let's just try, out of curiosity, before we move forward, let's just try to select, like I said before, the component for Australia instead of the largest one, which is component 137. And let's compute this over here, and now we'll find that the weakly connected components contain all countries within the community, but the community does not contain all countries within the component, so they are not equal. And for the overlap, we've got a few countries as well, like Mozambique or Somalia or Syria or Tajikistan. And yeah, that's it. So let's move forward to economical pressure. And economical pressure can be computed for our graph based simply on PageRank, because PageRank will, if you think about in degree, the number of incoming edges, PageRank is similar, but the incoming edges to neighbors will also contribute towards the PageRank of the node we are looking at. So this works as some kind of influence. If neighbors are more influent in the sense that they are more competed with, then if I get competition from a highly competed with neighbor, then I have a higher economical pressure as well. I believe this makes sense. And so we got the highest economic competition countries over here: Tuvalu, Kiribati, Nauru, Turks and Caicos Islands, Micronesia, British Indian Ocean Territory, Palau, Cook Islands. So again, these are many islands. And the least pressured countries, they are China, the US, Germany, Japan, South Korea, Italy, Netherlands, France, Mexico, etc. Okay. I hope you enjoyed, a bit of a different video where we focused on, lightly on network analysis. But I believe this common out neighbor score, which is quite intuitive, is also quite powerful as well. And so next time we'll take a look at MLOps, learning how to properly use MLflow to track, register, and version machine learning models. And we'll try to implement a cool A/B testing example for human-in-the-loop feedback, factoring in our Duck Lake as well. As usual, you'll be able to find the companion blog post for this video at datalabtechtv.com, which is based off of the Jupyter Notebook, but also contains additional information about the dataset and the ETL processes. You can now follow the channel on Blue Sky and join Discord to discuss topics like data science, MLOps or DevOps. You are quite welcome over there, so join Discord. It's very chill. There's not many people, so if you have any questions, I'll gladly answer them myself. And don't forget to drop a like and subscribe for all things data.